You are resting on something right now, and physics cannot tell you what it is. Not the chair, and not the floor underneath the chair, and not the ground underneath the building. All of that is made of atoms, and we know the atoms well. Underneath all of it, there is the space it all occupies, and that is the part nobody can name. For 300 years, that space was assumed to be a container. Absolute, immovable, simply there. Then Einstein made it bend and carry energy, and in 2015, we listened to it ring for 0.2 of a second after two black holes touched 1.3 billion years ago. So it is real. It is a thing you can push on. But here is what nobody mentions. Every single time physicists have looked more closely at that thing, they have found less of it, and something stranger underneath, and then run out of instruments. By the end of tonight, you will know exactly how far down that goes, and where the looking stops. Get comfortable. Hit subscribe if you're new here, because by the end of this, the ground under your feet is going to feel like an average rather than a fact. Now, let's slowly ease into this. Part 1. The floor you assume is there. There is a thing you have never once had to think about, and you are resting on it right now. Underneath you there is a floor. Underneath the floor there is a building, and underneath the building there is ground, and underneath the ground there is rock going down for thousands of kilometers until it becomes iron and pressure and heat. But underneath all of that, holding all of it, there is something else. There is the space it all occupies. There is the time it all happens in. And unlike everything else in that stack, you have never questioned it, because it has never given you a reason to. This is the oldest assumption in physics, and for a very long time, it was also the safest. Space is where things are. Time is when things happen. They are the container, and everything else is the contents. You can empty out a container, and it is still a container. You can take every object out of the universe, and what you would be left with, on this picture, is an enormous amount of empty space with nothing in it, sitting there, waiting. Isaac Newton wrote this down formally in 1687, in the book we usually just call the Principia. He said that absolute space, in its own nature and without relation to anything external, remains always similar and immovable. He said that absolute time flows equably, without relation to anything external. Read those two sentences slowly, and notice how strong they are. Without relation to anything external. Space does not care what is in it. Time does not care what happens in it. They are the stage. They are set before the play begins, and nothing the actors do can move them. Newton knew this was a bold claim, and he defended it with an experiment you could do this afternoon with a bucket. Take a bucket of water and hang it from a rope. Twist the rope tightly and let go. At first the bucket spins, and the water does not, and the surface of the water stays flat. Then, gradually, friction drags the water into rotation with the bucket, and as it begins to turn, the surface changes. It climbs the walls. It sinks in the middle. It settles into a curve. Now here is the part Newton wanted you to notice. At the moment the water is fully curved, the bucket and the water are turning together at the same rate. There is no relative motion between them at all. The water is not moving with respect to the bucket. It is not moving with respect to the room, particularly, because the room is going around too if you set the whole thing on a turntable. So what is the water responding to? What is it rotating relative to, such that it knows to climb the walls? Newton's answer was that it is rotating relative to space itself, not relative to the bucket, not relative to anything you can point at, but relative to the absolute, invisible, unmoving container. The curve in the water was, to him, direct physical evidence that the container is real and that you can detect your motion through it. Not everyone agreed. Gottfried Wilhelm Leibniz, writing letters back and forth with Samuel Clarke in the last years of his life, thought the whole idea was nonsense of a particularly seductive kind. Space, he argued, is not a thing. It is an order of coexistences. It is a way of describing the relationships between objects, and nothing more. When you say the cup is on the left of the plate, you are not making a claim about a container. You are making a claim about the cup and the plate. Follow that thought to the end, and you get something genuinely disorienting. If space is only the pattern of relationships between things, then remove all the things, and you do not get an empty room. You get nothing, not emptiness, not a void. There is no room left to be empty, because the room was never anything but the arrangement of the furniture. Leibniz died in November of 1716, which meant Clarke got the last word in their correspondence, and historians have pointed out that this probably shaped how the argument was received for the next century and a half. But the deeper reason the question went quiet is much simpler. Newton's version worked. It gave you the orbits of the planets. It gave you the return of comets. It gave you the tides, and the precise amount by which the Earth is flattened at its poles. When a framework is that accurate, nobody rushes to ask whether its foundations are philosophically sound. It stayed quiet for 200 years. Then, in the 1880s, an Austrian physicist named Ernst Mach picked up Leibniz's objection and aimed it directly at the bucket. Mach argued that the water is not responding to absolute space, because absolute space is not the kind of thing anything can respond to. It is responding to all the distant matter in the universe, every star, every galaxy, all of it, exerting a collective influence that defines what rotation even means. Take the rest of the universe away, Mach suggested, and spin the bucket, and nothing would happen at all. Mach could never turn that idea into equations, and it remains unproven and arguably unprovable in its strongest form. But he did accomplish one thing that mattered enormously. He made a young patent clerk in Bern deeply uncomfortable with the container. So that is where we start tonight, with a flaw, with the quiet, unexamined, entirely reasonable assumption that space is a place and time is a duration, and that the two of them are simply there, underneath everything, being the thing that everything else happens inside of. Hold on to that flaw, get a feel for how solid it is, because over the next 2 hours we are going to take it apart, one layer at a time, and every single layer is going to have less underneath it than the one before. Part 2. The century space-time became real. The first thing you should know about this story is that it does not begin with space-time dissolving. It begins with space-time becoming more real than anyone had ever imagined. In 1905, a 26-year-old working in a patent office in Bern took one experimental fact and followed it to its conclusion with a kind of stubbornness that is rare even among physicists. The fact was that light travels at the same speed for every observer, no matter how fast that observer is moving. This should be impossible. If you run toward a car, it approaches you faster. If you run away, it approaches you slower. Light does not behave this way. Chase a light beam at 9/10 the speed of light, and it still recedes from you at the full speed of light. Measure it from a train, from a planet, from a spacecraft, and you get the same number every time. Einstein took that seriously instead of trying to explain it away, and the first casualty was the word now. If the speed of light is universal, then two events that happen at the same moment for you do not happen at the same moment for someone moving relative to you. Not because one of you has a slow clock, because there is no fact of the matter. Simultaneity is not a property of the universe. It is a property of a point of view. The universal now, the single sweeping present moment that everything in existence shares, was the first piece of Newton's flaw to come away, and it came away in a single afternoon of reasoning. 3 years later, in 1908, a mathematician named Hermann Minkowski stood up at a conference in Cologne and told the audience something that must have sounded like poetry and turned out to be engineering. He said that from that point forward, space by itself and time by itself were doomed to fade away into mere shadows, and only a union of the two would preserve an independent reality. That union is what we call spacetime, and it is worth pausing on how recent that is. The word spacetime is younger than the airplane. For all but a rounding error of human history, nobody had the concept at all. Then in 1915, Einstein did something considerably stranger than removing the universal now. He made the container move. The field equations of general relativity say that matter and energy tell spacetime how to curve, and the curvature of spacetime tells matter and energy how to move. That is a two-way relationship, and it is the end of the container as a container. The stage is no longer set before the play. The stage is one of the actors. Put a mass down, and the geometry around it changes shape. Move the mass, and the change propagates outward. What Newton had described as a rigid, immovable backdrop was now a flexible, responsive, physical thing. The first confirmation came 4 years later. On the 29th of May 1919, expeditions led by Arthur Eddington photographed stars near the edge of the sun during a total eclipse to see whether their apparent positions had shifted. Einstein predicted that light grazing the solar limb would be bent by about 1.75 arcseconds, which is roughly twice what you would get from Newtonian gravity, treating light as a stream of particles. The measurements came in on Einstein's side. When the result was announced at a joint meeting of the Royal Society and the Royal Astronomical Society on the 6th of November 1919, a man who had been essentially unknown outside physics became, within about a week, the most famous scientist alive. You use this result constantly, and you have never thought about it. The satellites in the global positioning system carry atomic clocks, and those clocks sit higher in the Earth's gravitational field than you do, where spacetime is stretched less severely. As a result, they run fast by about 45 microseconds per day. They are also moving quickly in orbit, which slows them by about 7 microseconds per day. The two effects do not cancel. If the system did not correct for both of them, your position would drift by something on the order of 10 kilometers every single day. Every time your phone tells you which street you are on, it is doing so by accounting for the shape of space-time. But the result that made space-time feel most solid of all came almost exactly a century after Einstein wrote the equations. It is the 14th of September 2015, and it is 9:50 in the morning and 45 seconds, universal time. In a building in Livingston, Louisiana, there is an instrument in the shape of an enormous L. Each arm is 4 kilometers long. Down each arm, a laser beam is traveling out to a mirror and coming back, over and over, and the two returning beams are being compared against each other with a precision that has no equivalent anywhere else in human engineering. Nothing in the building is moving. The night shift is quiet. The air conditioning is running. And then something arrives that has been traveling for 1.3 billion years. It does not knock anything over. It does not make a sound. It passes through the roof, through the ceiling, through the instrument, through the floor and the foundation and the soil beneath it, and it passes through every person in the building without any of them feeling the slightest thing. What it does is stretch one arm and squeeze the other, and then reverse again, a few times over about 0.2 of a second. The amount of stretching is 1 part in 10 to the 21st. Across 4 kilometers, that is a change in length smaller than 1,000th of the width of a proton. It is as though you measured the distance to the nearest star and detected a change the width of a human hair. 7 milliseconds later, the same thing happens in Hanford, Washington, 3,000 kilometers away. That gap is exactly what you would expect if something had swept across the surface of the Earth at the speed of light. What arrived was the last fraction of a second of a collision. Two black holes, one about 36 times the mass of the Sun and one about 29, had spiraled into each other and merged into a single black hole of about 62 solar masses. Do the arithmetic, and 3 solar masses are missing. Those 3 solar masses were not converted into light, or heat, or matter. They were radiated away as pure disturbance in the shape of spacetime, and during the fraction of a second it took, that collision was putting out more power than every star in the observable universe combined. Sit with what that measurement establishes, because it matters for everything that follows. Spacetime is not a passive backdrop. It is something you can push on. It carries energy. It can be disturbed, and the disturbance travels, and it travels at a specific speed, and it eventually settles down. In the technical language, it has degrees of freedom of its own. Those 2 black holes spiraled inward in the first place, precisely because they were bleeding energy into spacetime as they went. If spacetime could not carry energy away, they would have orbited each other stably, forever. So by the middle of the 20th century, and overwhelmingly by 2015, the situation was this. Newton's inert container had become the most physically real object in the whole of physics. It bends, it ripples, it rings like a struck bell, and then goes quiet. It is not the emptiness between things. It is a thing. Which is exactly why what happened next was so unwelcome. Because once you have established that something is a real physical object with its own dynamics, there is an obvious next step. Physics has a standard procedure for real physical objects. It is the most successful procedure anyone has ever devised, and when they turned it on spacetime, it did not work, and it has not worked since. Part 3. 3 ways to break the best tool in physics. Physics has one universal move, and it has worked every single time it has been tried, on every single thing it has been tried on, except one. The move is called quantization. You take a classical description of something, a description in which quantities vary smoothly and continuously, and you rebuild it as a quantum description, in which the quantities come in discrete amounts and behave probabilistically. It sounds abstract. It is the most productive idea of the 20th century. Electromagnetism went first. The classical theory of electric and magnetic fields was rebuilt as quantum electrodynamics, and the result is, by a wide margin, the most precisely verified theory in the history of science. Take the magnetic moment of the electron. Quantum electrodynamics predicts a value, experimentalists measure a value, and the two agree to roughly 1 part in a trillion. To give that a physical sense, it is the equivalent of measuring the distance from New York to Los Angeles and being off by about the width of a human hair. Not the width of your hand, the width of one hair. The strong nuclear force followed. The weak nuclear force followed. By the 1970s, all 3 had been folded into a single framework called the Standard Model, which has since predicted new particles in advance and had them found, most recently, the Higgs boson in 2012. 3 forces down, 1 left. Gravity has resisted quantization for approximately 90 years, and here is the part that matters for tonight. It has not resisted in one way that people keep failing to solve. It has resisted in 3 separate and distinct ways, and the 3 failures are structurally different from each other, and they all point in the same uncomfortable direction. So we are going to take them one at a time. The first failure is technical, and it goes by the word non-renormalizable. In quantum field theory, calculations produce infinities constantly. You go to compute something ordinary, and the answer comes back as infinity, which is not a number and not an answer. Physicists developed a procedure for handling this, called renormalization, and although Richard Feynman himself described it as a dippy process and suspected it was mathematically illegitimate, it works with extraordinary precision. The trick is that all the infinities can be swept into a small fixed number of quantities that you measure experimentally anyway, like the mass of the electron and the strength of its charge. You measure those, you plug them in, and everything else the theory predicts comes out finite and correct. The reason it works is a matter of dimensions. The numbers that set the strength of electromagnetism and the nuclear forces have the right dimensional character for the infinities to be absorbable a finite number of times. Newton's gravitational constant does not. Its dimensions mean that when you go to the next order of precision in a gravitational calculation, you do not encounter the same kinds of infinity you already dealt with. You encounter new kinds, and at the order after that, new kinds again. Each new kind requires its own independent experimentally measured number, and the sequence never terminates. For years this was suspected but not proven. Then in 1985, Mark Goroff and Augusto Sagnotti carried out a calculation so laborious that it required computer algebra techniques that barely existed at the time, and showed that pure gravity produces a divergence at what is called two loops, which genuinely cannot be absorbed. Sit with what that means. A theory that requires an infinite number of experimentally measured inputs before it can make a single prediction is not a difficult theory. It is not an incomplete theory. It is an empty one. You would have to measure the universe infinitely many times to predict anything about it once. Quantized general relativity, taken as a fundamental theory, does not fail to give the right answer. It fails to give any answer at all. There is one escape route that has never been fully closed off, and it is worth mentioning because it shows how seriously people have taken this. In 1976, Steven Weinberg proposed that gravity might be what he called asymptotically safe, meaning that, although the theory looks hopeless when you approach it the standard way, the infinite proliferation of parameters might collapse at very high energies onto a small finite set. If that turned out to be true, gravity would be quantizable, after all, just not by the route everyone had tried. Nearly 50 years later, the proposal is still open, still being investigated by a small and determined community, and still unproven. It is a live possibility rather than a solution, and the honest summary is that the field has not been able to close the question in either direction. The second failure is not technical. It is conceptual, and it is considerably worse. If you take general relativity and apply the standard quantization machinery to the whole universe, rather than to a small piece of it, you arrive at an equation written down by Bryce DeWitt in 1967, building on work by John Wheeler. There is a story, probably improved in the retelling, that the two of them worked it out in an airport lounge, and afterwards, DeWitt called it the Wheeler equation, and Wheeler called it the DeWitt equation, each trying to hand the credit to the other. Today we call it the Wheeler-DeWitt equation. In its compressed form, it says that the Hamiltonian operator, acting on the wave function of the universe, equals 0. You do not need to know what a Hamiltonian operator is in detail. You need to know one thing about it. The Hamiltonian is the operator that generates evolution in time. It is the mathematical object whose entire job is to say how a system changes from one moment to the next. And in the fundamental equation for the universe as a whole, it is set equal to 0, which says that the wave function of the universe does not evolve. There is no time variable in the equation, not a slow one, not a strange one, none. Described quantum mechanically and taken as a whole, the universe is static. Physicists have been arguing about what that means for nearly 60 years, and there is still no consensus. Some argue that time is not fundamental, but emerges as a correlation between subsystems, so that what we call the passage of time is really one part of the universe changing relative to another part, with no external clock anywhere. Julian Barbour has spent a career arguing something stronger, that time simply does not exist, and that the appearance of flow is something our physics has been importing without noticing. Others regard the equation as evidence that the quantization procedure itself was applied wrongly. Notice that nobody in that list is arguing the equation is fine. The third failure is the deepest, and it gets discussed the least, probably because it is the hardest to make vivid. It is called background dependence. Quantum field theory is built on a stage. You specify a spacetime first, then you define fields as objects that take a value at every point of that spacetime, and then you quantize the fields. The stage is the thing you need in place before you can begin. Every calculation in the framework presupposes it. General relativity says the stage is dynamical. The stage bends, ripples, and responds. The stage is one of the actors. So to write a quantum theory of gravity in the standard way, you would need to define a quantum field on a spacetime, where the thing you are trying to describe is the spacetime. The tool requires as an input precisely the object it is being asked to produce as an output. This is not a calculation that comes out wrong. It is a request that cannot be phrased. Now step back and look at the three of them together, because the pattern is the point. The first failure says that if you treat spacetime as a quantum field like any other, the theory carries no predictive content. The second says that if you quantize the whole thing honestly, time disappears from the description. The third says that the mathematical language you would use presupposes the very thing you are trying to explain. These were not three attempts at the same wall. They came from different physicists, using different methods, arriving at different decades. And in every case, the harder anyone looked at spacetime, the less spacetime there was to find. There is one important caveat, and it should be said clearly, because otherwise this sounds more dramatic than the situation is. None of this affects anything you will ever experience. General relativity works beautifully as an approximation at any energy you are likely to encounter, in the same way that the physics of water works beautifully without anyone needing to think about quarks. The failure only shows up when you push toward the extreme, toward the very small and the very energetic. Physicists have a formal way of saying this, called effective field theory, and it is why nobody noticed the problem for the first 20 years. But an approximation is an approximation of something, and that is the question this whole story turns on. For decades, the response to these three failures was to try harder. Better mathematics, cleverer quantization schemes, new frameworks. What nobody was seriously considering, because it sounded absurd, was the possibility that the procedure was failing for a reason. That you cannot quantize spacetime for the same reason you cannot quantize a traffic jam or a price index. That it is not the kind of thing that has quanta, because it is not the kind of thing that is fundamental. Nobody was thinking that way in the 1970s. And then a graduate student asked his supervisor a question about a cup of tea. Part 4. The Cup of Tea and the Black Hole. In 1972, at Princeton, John Wheeler said something to one of his graduate students that he probably intended as a joke. The student was Jacob Bekenstein. Wheeler had a habit of posing small, mischievous puzzles to see what people would do with them, and the one he handed Bekenstein went roughly like this. Suppose you have a cup of hot tea. Hot tea has high entropy, because entropy is a measure of disorder, and the molecules in hot tea are in an enormous number of possible arrangements. Now suppose you drop the cup into a black hole. Wheeler said that when you do this, you commit what amounts to a perfect crime, because the evidence is gone forever. The entropy has left the universe. The problem with that is the second law of thermodynamics, which says the total entropy of a closed system never decreases. It is the closest thing physics has to an unbreakable rule. Arthur Eddington once wrote that if your theory is found to be against the second law, there is nothing for it but to collapse in deepest humiliation. And here was a perfectly ordinary physical process, dropping something into a hole, which appeared to violate it completely. The reason the entropy seems to vanish is a result that had been proven only a few years earlier, and which physicists found beautiful at the time. A black hole, once it has settled down, is described completely by exactly three numbers: its mass, its electric charge, its angular momentum. That is the entire list. Two black holes with the same three numbers are identical in every respect, no matter what fell into them. One could have formed from a collapsing star, the other from an equivalent mass of encyclopedias, and there is no measurement you can perform that would tell them apart. This is usually called the no-hair theorem, on the grounds that a black hole has no distinguishing features. So the T goes in, the black hole gets slightly heavier, and everything else about the T is simply gone. Not hidden, gone from the description. Bekenstein looked at this and drew a conclusion that his supervisor had not intended, and that essentially the entire field found unacceptable. He said that if entropy cannot be destroyed, and the T's entropy went into the black hole, then the black hole must be carrying that entropy. Black holes must have entropy of their own. And, working through the argument, he found that the entropy would have to be proportional, not to the volume of the black hole, but to the area of its event horizon. Almost nobody believed him. The paper had a difficult time with referees, and was eventually published in Physical Review D in 1973. But the resistance from senior physicists was substantial, and it was not subtle. The loudest objection came from Stephen Hawking, and it was not a vague objection. It was a specific, technically sharp, and apparently fatal one. The argument goes like this. In thermodynamics, entropy and temperature are not independent concepts. They are locked together. If a thing has entropy, it has a temperature. And if a thing has a temperature above absolute zero, then it radiates. Everything with a temperature glows, in some part of the spectrum. Your body is radiating infrared right now. A black hole, by its definition, is a region from which nothing escapes. So a black hole cannot radiate. So a black hole cannot have a temperature. So a black hole cannot have entropy. Therefore, Bekenstein is wrong. That is a clean piece of reasoning, and it was widely regarded as settling the matter. Hawking then did something that is one of the reasons his name is known outside physics. He went to prove it rigorously, and in 1974 he came back with the opposite result. What he did was apply quantum field theory to the region immediately around an event horizon in a curved spacetime, which nobody had properly done before. And the calculation said that black holes radiate, not by anything escaping from inside, but through a subtle process involving the quantum vacuum near the horizon, which is not empty in the way the word suggests. The upshot is a steady trickle of particles flowing outward, carrying energy away, at a well-defined temperature. The temperature is inversely proportional to the mass. Bigger black holes are colder, smaller ones are hotter. Run the numbers on a realistic case, and you get something almost comically faint. A black hole with the mass of the Sun has a temperature of about 60 billionths of a Kelvin. The cosmic microwave background, the leftover warmth of the early universe that fills all of space, sits at about 2.7 Kelvin, which means every astrophysical black hole in existence is enormously colder than the space around it, and is therefore absorbing far more energy than it emits. None of them are shrinking. They will not begin to until the universe itself has cooled below their temperature, which is a very long way off. A solar mass black hole, left completely alone, would take something on the order of 10 to the 67th power years to evaporate, against a current age of the universe of about 14 billion years. There is a crossover point, and it is a strangely homely number. Because temperature rises as mass falls, there is a particular mass at which a black hole's temperature matches the 2.7 Kelvin of the surrounding universe, and above which it absorbs more than it emits. That mass is roughly the mass of the Moon. Every black hole heavier than the Moon is currently growing. Every black hole lighter than the moon, if any exist, is currently shrinking, and shrinking accelerates as it goes, because losing mass makes it hotter, which makes it lose mass faster. The final stage of that process is not a fade, it is a burst. But the faintness is not the point. The existence is the point. Because Hawking's calculation did not merely confirm that black holes have a temperature. When he worked out the corresponding entropy, it matched Bekenstein's proposal exactly, and it fixed the proportionality constant that Bekenstein had been unable to pin down. The result, now called the Bekenstein-Hawking entropy, says that the entropy of a black hole is precisely 1/4 of the area of its event horizon, measured in Planck units. There is a detail here that is easy to skate past and worth stopping on. Hawking set out to destroy this idea and ended up establishing it, using his own calculation against his own expectation. That does happen in physics, but not often, and it is one of the cleaner examples of a theorist being overruled by his own arithmetic. What nobody quite appreciated at the time is that they had just been handed a clue about something much larger than black holes. Because this was the first moment in the history of physics when gravity started behaving like thermodynamics, not resembling it loosely, obeying it with laws that map 1-to-1 onto the classical laws of heat. And thermodynamics has a particular reputation among physicists. It is what you get when you describe something enormously complicated without resolving its parts. It is the physics of not looking too closely. You can describe sound waves in a gas with beautiful precision without ever mentioning a single molecule. Keep that comparison somewhere in the back of your mind. We are going to come back to it, and when we do, it is going to stop being a comparison. For now, the situation is this. Bekenstein was right, Hawking proved it, and everyone moved on to the next question, which was a mistake, because the answer they had just written down had something wrong with it, and the wrongness was hiding in plain sight, in the shape of the formula itself. Part 5. The number that should not be there. To see what is wrong with the formula, you have to understand what entropy is actually counting, and it is not disorder. Disorder is a teaching metaphor that does more harm than good past a certain point. Entropy counts arrangements. Specifically, it counts how many distinct microscopic configurations of a system would look identical from the outside. If you have a room with 100 air molecules in it, and you specify only the temperature and the pressure, there is an enormous number of different ways those 100 molecules could be positioned and moving that would all produce the same temperature and pressure. Entropy is, essentially, the logarithm of that number. It measures how much detail you are not specifying. It is a count of hidden information. Now here is the property that matters, and it is so ordinary that in 3 centuries of thermodynamics, essentially nobody thought to question it. Entropy scales with volume. Take a box of gas, double the size of the box while keeping the density the same, and you have doubled the number of molecules, and therefore roughly doubled the entropy. Double it again, double again. The relationship holds for gases, for liquids, for solids, for plasma, for anything made of parts distributed through a region. The amount of hidden information in a thing is proportional to how much thing there is. This is not a law anyone had to fight for. It is arithmetic. More stuff, more arrangements. A black hole does not do this. The Bekenstein-Hawking formula says that the entropy of a black hole is 1/4 of the area of its event horizon in Planck units, not the volume it encloses, the area of the boundary around it. And that is genuinely strange. If you double the radius of a black hole, its volume increases by a factor of 8, but its area only increases by a factor of 4, and it is the 4 that the entropy follows. The amount of information a region of space can hold is set by the size of the surface wrapped around it, not by how much room is inside. Let me put you inside that so it stops being an equation. Imagine shrinking. Not gradually, Just accept that it has happened, and you are now floating a short distance outside the event horizon of a black hole with the mass of the Sun. The horizon in front of you is a sphere about 3 kilometers across, and it is not a surface in the sense of a wall. There is nothing there to touch. It is simply the boundary past which every possible path leads inward. Now imagine the whole of that sphere marked out into tiles, the way a dome might be tiled, except that each tile is one Planck area across. A Planck area is about 2.6 times 10 to the minus 70 square meters. To give that a sense of scale, if you took a single proton and asked how many Planck areas would tile its cross-section, the answer is around 10 to the 40. This is smaller than small. This is the scale at which the words distance and area may stop meaning anything. And you begin counting tiles. Each one, roughly, holds one bit. One yes or no. One binary distinction about the black hole's internal state. You count past the number of bits it would take to describe every atom in a human being. You count past the number it would take to describe the Earth. You count past the total information content of the star that collapsed to make this thing in the first place, and you are not close to finished, because you have passed that mark by something like 20 orders of magnitude, and the tiles keep going. When you finish, the number you have is around 10 to the 77. And then you turn around and look at the interior, the enormous, 3-kilometer wide, fully three-dimensional volume, enclosed by the sphere you just counted. It adds nothing, not a single bit. Everything there is to know about this object was already written on the surface you were standing on. It is worth sitting with how far apart those two numbers are, because the gap is the whole story. The star that collapsed to form this black hole was made of something like 10 to the 57 particles, and describing all of them completely would take a number of bits somewhere around 10 to the 58. The black hole it became holds around 10 to the 77. That is not a modest increase. That is a factor of 10 to the 19. The collapse did not destroy information. It multiplied the amount of hidden information by something like 10 billion, and it did so while the object got physically smaller and simpler to describe from the outside. Something is being counted in there that was not being counted before, and whatever it is, it lives on the surface. There is also a purely geometric reason this should have alarmed people immediately. Areas and volumes grow at different rates, and the difference compounds without limit. For a region a meter across, the mismatch between the two scalings is unremarkable. For a region the size of a galaxy, the volume has run away from the area by a factor so large that if entropy really did scale with volume in general, the maximum information content of ordinary space would exceed the black hole bound by an amount that has no comfortable name. That cannot happen, because you can always add mass and force a collapse. So it is not that black holes are the exception to volume scaling. It is that volume scaling was never right, and black holes are simply where the error became visible. Scale that up, and it gets worse. Sagittarius A star, the black hole at the center of our own galaxy, is about 4.3 million times the mass of the Sun. Its entropy is larger than the entropy of all the ordinary matter in the observable universe put together. One object, one surface, more hidden information than everything made of atoms, everywhere we can see. Now, here is why this should bother you personally rather than academically. Bekenstein realized fairly quickly that this could not be a fact about black holes alone. He formulated what is now called the Bekenstein bound, and the reasoning behind it is uncomfortably simple. Suppose you had a region of space containing more information than the equivalent black hole of that size. You could then, in principle, add mass to that region until it collapsed into a black hole, and the entropy would have to go down in the process, which the second law forbids. So no region can exceed the bound. Every region of space has a maximum information content, and it is set by the area of the surface enclosing it, including the region you are sitting in. There is a maximum amount of information that can exist inside your body, and it is not determined by your volume. It is determined by your surface. Every arrangement of every atom in you, every configuration of every electron, the entire specification of what you physically are, is bounded by the area of a surface you could wrap around yourself. Not by how much of you there is, by how much of you is on the outside. That is not a metaphor about the soul or a poetic flourish about skin. It is a counting argument, and it comes from the second law of thermodynamics, and physics currently does not know how to avoid it. The numbers involved are so far from anything you would ever run into that the bound is in no danger of being reached. A human body's actual information content is somewhere in the vicinity of 10 to the 28 bits, depending on how you count, and the bound on a region your size is closer to 10 to the 69. You are using a vanishingly small fraction of your allowance, but the existence of the allowance is what matters, and the fact that it is calculated from your surface rather than from your insides is what should stop you. Think about what that would mean if you tried to fill it. To reach the maximum information content of the space you occupy, you would have to compress that much detail into that much room, and long before you got there, the region would collapse. The universe does not have a way of storing more than a certain amount of specification in a given place, and when you try, it responds by forming a horizon. Information density and gravity turn out to be the same subject, and nobody expected that. And notice what it implies about the interior of things. If the outside surface sets the limit, then the inside is not carrying independent information. Whatever is in there is, in some sense that nobody in 1974 could have made precise, already accounted for by the boundary. Jacob Bekenstein died in 2015, a few months before LIGO detected its first gravitational wave, and before the results that would eventually explain where his area law comes from. He spent 40 years being right about something whose significance nobody, including him, fully understood at the time. Because if entropy scales with area rather than volume for every region of space, and not just for black holes, then somebody is eventually going to ask the obvious question. If everything inside a region can be accounted for by its boundary, what exactly is the inside for? Part 6. Let us put the pieces together. We are about halfway through, and this is a good moment to stop walking downward and stand still for a minute, because 4 separate things have been established, and it is worth seeing them side by side before we go further. The first thing is that spacetime is real in the strongest sense physics has. It bends measurably, it carries energy demonstrably, and in 2015, we watched it ring. Whatever else is true, it is not a convenient fiction, and it is not merely a coordinate system. Something is there. The second thing is that the standard procedure for describing real physical things, quantum mechanically, does not work on it, and does not work in 3 independent ways. It produces a theory with no predictive content. It produces an equation from which time has disappeared, and it requires as its starting ingredient exactly the thing it is supposed to explain. Those 3 failures came from different people in different decades using different methods. The third thing is that black holes obey the laws of thermodynamics, precisely and in detail, which is a peculiar thing for a region of curved spacetime to do. Thermodynamics is what physics uses when it is describing enormous numbers of small things without tracking them individually. And the fourth thing is that the entropy came out proportional to area rather than volume, which is not how anything else in nature behaves, and which appears to hold not only for black holes, but for every region of space, including the one you are in. Now, here is what makes those 4 things worth stacking up. None of them was looking for the others. Bekenstein was trying to save the second law from a cup of tea. Hawking was trying to prove Bekenstein wrong. Goroff and Sagnotti were doing a 2-loop calculation to settle a technical question about divergences. DeWitt was applying a standard quantization procedure and reporting what came out. 4 investigations, 4 motivations, none of them coordinated, none of them aimed at the nature of spacetime as such. And every one of them, in its own way, came back with the same message. When you look closely at spacetime, you find less of it than you expected, and what you find behaves like a summary of something you cannot see. There is a useful comparison from an earlier era. In the 1800s, several unrelated lines of inquiry kept implying that matter came in discrete pieces. Chemists noticed that elements combine in fixed whole number ratios. Physicists studying gases found that pressure and temperature behaved exactly as they would if the gas were made of countless tiny colliding objects. Botanists watching pollen grains jitter in water could not explain the jitter any other way. None of those people were trying to prove atoms existed, and several of them did not believe in atoms. The convergence did the work. That is a pattern, and patterns like that are how physics usually finds its way into a new picture. When the same conclusion keeps arriving from unrelated directions, the conclusion is usually about the subject rather than about the methods. But notice what we still do not have. We have 4 pieces of circumstantial evidence and no mechanism. Nobody has yet said what space-time would be made of if it is made of something, or how the making would work, or why the area law takes the specific form it does. We are still not in a position to say what space-time is. What happens next is that somebody takes the 4th piece, the area law, and stops treating it as a curious property of black holes. Somebody asks what happens if you take it completely literally and apply it not to a collapsed star, but to everything. Part 7. Everything inside fits on the outside. The person who took it literally first was Gerard Hooft in 1993, and the reason he took it literally is that he had been staring at black holes for years and had concluded that they were the sharpest available clue about anything. His argument, developed further by Leonard Susskind the following year, runs as follows, and it is short enough to state completely. The Bekenstein bound says the maximum information in any region of space is set by the area of the surface enclosing it, not approximately set, exactly set, with a specific formula. Now, information is not decoration. Information is what a physical description consists of. If you fully specify the information in a region, you have fully specified everything about it. So if the maximum information in a region is given by a number attached to its boundary, then everything that region can possibly be doing is expressible as something happening on that boundary, which means the interior of any volume of space carries no independent information at all. They called it the holographic principle, after the optical holograms that store a complete 3-dimensional image in a flat piece of film. Turn the film, and the image turns. Move your head, and you see around the objects. All of that dimensionality is encoded in a 2-dimensional surface, in the interference pattern of light, and you can recover it because the encoding is complete. The analogy is worth understanding properly, rather than taking on trust, because it is doing real work. An optical hologram is made by splitting a laser beam in 2. One half goes straight to a photographic plate. The other half bounces off the object first and then hits the plate, arriving slightly out of step with the first because it traveled a longer and more complicated path. Where the 2 halves meet, they interfere, and the plate records the resulting pattern. What is stored is not a picture. If you look at a developed holographic plate, you see something that resembles a smear of fine rings, and nothing like the object. But shine the original kind of light back through it, and the 3-dimensional image reassembles in the air, because the phase information, the record of how far every part of the light traveled, was preserved in that flat pattern. The point that matters is that no depth was thrown away. The plate is two-dimensional, and it contains a complete specification of a three-dimensional scene. That is the feature Tooft and Susskind were reaching for. Depth need not be stored as depth. It can be stored as a pattern on a surface, and recovered. Where the analogy breaks down is worth noting too, because physicists use it despite its flaws. An optical hologram is a recording of light that bounced off an object. The object is still there, and is still three-dimensional. The holographic principle is a stronger claim, that the boundary description is not a recording of an interior, but an equally valid and possibly more fundamental account of the same physics. There is no separate object sitting behind it. Now, it is important to be precise about the claim because it gets garbled constantly, usually in ways that make it sound both more exciting and less interesting than it is. The claim is not that the world is an illusion. It is not that you are a projection, or a picture, or that the room you are in is fake. Everything in the interior is entirely real and behaves exactly as it appears to behave. You can walk through it, measure it, be injured by it. The claim is that the interior description is redundant. There is another description, in fewer dimensions, on a surface, which contains all the same information and is possibly the more fundamental of the two. Both are accurate. They describe the same physics, but one of them has fewer dimensions in it than the other, and if you had to guess which one nature is running, you would not guess the one carrying the extra baggage. It is worth knowing how Hooft arrived here, because it was not by admiring the elegance of the counting. He had spent years on the question of what happens to things that fall into black holes, and had become convinced that the standard picture could not be right, because it implied that the details of what fell in were erased from the universe in a way quantum mechanics forbids. He kept concluding that the description of the interior had to be recoverable from the horizon, because there was nowhere else for it to be. The holographic principle was, for him, less a bold generalization than the only remaining option. Susskind arrived from a different direction, through string theory, and has said that when the two lines met, he recognized immediately that they were the same idea. What is notable is that both men reached it while trying to solve a specific and narrow problem, and both were surprised by how far the conclusion reached. Try it on the room you are actually sitting in. Draw an imaginary sphere around it. Everything inside that sphere, every molecule of air, every object, the chair, the walls, your body, every electrical signal running through your nervous system right now, every photon in transit between the light source and your eye, the whole running state of everything inside that boundary. The holographic principle says that all of it can be encoded on the surface of that sphere, at the resolution of about 1 bit per Planck area, and that this encoding leaves nothing out. The inside of the room has 3 dimensions. The surface has 2. The 2-dimensional version is not a summary or a lossy compression. It is complete. There is a version of this that makes the counting argument feel less abstract, and it comes from asking what happens if you refuse to believe it. Suppose the maximum information really did scale with volume, as it does for every ordinary substance. Then take a region and start filling it with information as densely as physics allows. Store more and more, pack it tighter. Information has to be carried by something physical, and physical things have energy, and energy gravitates. As you approach the maximum density permitted by the volume scaling rule, the mass energy in the region becomes enormous, and before you can ever reach that maximum, the region collapses into a black hole, which means you never get to test volume scaling. The universe stops you. The moment you try to exceed the area-based bound, geometry itself intervenes and forms a horizon, and the resulting object has an entropy given by its area, exactly as Bekenstein said. So the bound is not a rule imposed from outside. It is what gravity does. Push the information density past the limit, and you get a black hole, and the black hole obeys the limit. That is a remarkable thing for a theory of geometry to be doing. Gravity is behaving like a filing system with a maximum capacity and enforcing it. You can run the same calculation on the largest region we have access to. The observable universe is a sphere with a radius of about 46 billion light-years, and if you take its surface area and divide by the Planck area, you get a maximum information content somewhere in the region of 10 to the 123 bits. That number is the answer to a question nobody used to think had an answer. How much can happen? Not how much matter is there, not how much energy, but how many distinct physical states are available to everything we can see, ever. It is finite, large past any use, but finite, and set by a surface. And that finiteness is itself a result worth pausing on. In the Newtonian picture, there was no limit of this kind at all. Space was a container of unlimited capacity. You could always specify a position more precisely, always add another decimal place, always store a little more. The holographic bound says no. There is a ceiling, it is calculable, and it depends on the area around you rather than the room you have. Something is enforcing a budget, and nothing in the container picture has any business having a budget. Susskind has described the implication in a way that is worth repeating because it is honest about how strange it is. If the holographic principle is correct, then the three-dimensionality of the world is not fundamental. Depth, the direction you look into when you look across a room, is emergent. There is a description of everything that has one fewer dimension than the one you are living in, and the extra dimension is something like a way of organizing the information rather than a place. For 4 years, this was a beautiful guess that nobody could use. That needs saying plainly, because in retrospect, the story looks like a smooth progression, and it was not. From 1993 to 1997, the holographic principle was an argument based on counting. It said that the information had to fit on the boundary. It did not say how. Nobody could take a physical situation in the interior, translate it into the boundary language, do a calculation, and translate back. There was no dictionary. There was a claim that a dictionary must exist. It is also fair to ask what would have to be true for the principle to be wrong, because a claim that cannot fail is not worth much. There are a few clean ways it could have gone. If someone found a physical situation where information could be packed into a region past the area bound without a horizon forming, the argument would collapse immediately. If black hole entropy turned out to scale with volume after all under some more careful treatment, the foundation would go. If the entropy of a black hole could be accounted for entirely by degrees of freedom sitting inside rather than on the boundary, the interpretation would change completely. None of those has happened, and people have looked hard, particularly at the third one. But they are real tests rather than rhetorical ones, and the principle has survived them rather than being immune to them. And there were reasons to doubt it. The whole argument rested on the Bekenstein bound, which rested on the black hole entropy formula, which rested on Hawking's calculation in a regime nobody had ever tested experimentally and never will. A tower of theory with no measurement anywhere in it. Hooft himself has always been careful about this, and has spent much of his career arguing for interpretations of quantum mechanics that most of his colleagues reject, which is worth knowing when you weigh his confidence. There is also a specific reason to worry that has to do with what kind of space you are in. The whole counting argument assumes a well-defined boundary that you can wrap around a region and measure the area of. That works fine for a sphere in a room. It works less well for the universe as a whole, which does not obviously have an outside, and it works differently depending on how the universe is curved. Hold on to that concern. It is going to come back at the end of the night, and it is going to be the largest unresolved problem in the entire subject. But in 1996, the situation was this: 3 failures of quantization, 1 anomalous entropy law, 1 suggestive principle claiming that reality has 1 fewer dimension than it appears to, and no mathematics connecting any of it. we were still not in a position to say what spacetime is. And then, in November of 1997, a 30-year-old physicist at Harvard posted a paper that did not argue that a dictionary should exist. He wrote one. Part 8. The Dictionary. The paper appeared on the 27th of November, 1997, under a title that gives away nothing at all to a general reader. Its author was Juan Maldacena, then in his early 30s and working at Harvard. Within a few years, it would become the most cited paper in the history of high-energy physics, with a citation count now well past 20,000, which in a field this size is not a record so much as a category of its own. What it proposed was this. Take a particular kind of spacetime, called anti-de Sitter space, with 5 dimensions. Anti-de Sitter space is not our universe. It is a mathematically convenient universe, with a specific negative curvature, shaped in a way that gives it a well-defined boundary out at infinity that you can actually talk about. Now put a full theory of quantum gravity in there, specifically string theory. Separately, take the 4-dimensional boundary of that space and put on it a particular quantum field theory, an ordinary one, of the kind physicists already knew how to work with. Crucially, a theory with no gravity in it whatsoever, and one fewer spatial dimension. It helps to have a picture of anti-de Sitter space, because the name is doing it no favors. Imagine the inside of an enormous cylindrical can. You are floating somewhere in the middle. The curvature of this space has an unusual effect. It acts a little like a valley, so that if you throw a ball away from the center, it slows, turns around, and comes back to you, no matter how hard you throw it. You cannot escape the middle by throwing things. But light behaves differently. Light in this geometry can reach the wall of the can and come back in a finite amount of time, not an infinite journey, a round trip you could time with a stopwatch. That is the property that makes everything possible. Because light can get out to the edge and return, the edge is not an unreachable abstraction. It is in causal contact with everything inside. Whatever happens in the middle of the can, in principle, be read off at the wall. Our universe does not work like this, and we will come back to why that matters enormously. But in anti-de Sitter space, there is a wall, and the wall can be written on. Maldacena's proposal was that these two theories are the same theory, not analogous, not similar in structure, not related by an approximation that holds in some limit, equivalent. Every physical question you can pose in the 5-dimensional gravitational theory has an exact translation into a question in the 4-dimensional theory without gravity, and when you compute the answers on both sides, they match. 2 completely different-looking descriptions, using different mathematics, in different numbers of dimensions, one containing gravity and one not, turn out to be 2 ways of writing down the same physics. This is what a dictionary means, not a metaphor, not a rough correspondence, but an actual translation table. Black holes in the interior correspond to hot states of the boundary theory. A particle falling inward corresponds to a particular kind of spreading out on the boundary. The correspondence has been checked in an enormous number of specific cases over almost 30 years, and it keeps working. It is worth being clear about how unusual a claim of exact equivalence is, because physics is full of approximate relationships, and this is not one of them. When 2 descriptions are equivalent in this sense, physicists call it a duality, and dualities have a particular character. They are not saying that one description is true and the other is a useful fiction. They are saying that the question of which is the real one has no answer, because there is no measurement that could distinguish them. Both are complete. Both give every correct prediction. They are the same physics, wearing different clothes. And there is a translation table, which is where the word dictionary earns itself. A field in the boundary theory corresponds to a particular kind of disturbance propagating in the bulk. The temperature of the boundary theory corresponds to the presence of a black hole in the bulk, with the black hole's temperature matching. The distance into the bulk, the depth of the fifth dimension, corresponds on the boundary side to a scale of energy. Things deep inside the can correspond to low energy, large scale, coarse features of the boundary theory, and things near the wall correspond to high energy, small scale, fine detail. Read that last one again, because it is quietly the strangest entry in the whole table. Depth in the bulk is energy scale on the boundary. The direction you would walk in, if you were inside the can, corresponds on the other side of the dictionary to nothing spatial at all. It corresponds to how finely you are looking. The response of the field is not something you can convey with a citation count, so here is the scene. It is the summer of 1998, at the annual Strings Conference, held that year in Santa Barbara. The room is full of theoretical physicists who have spent the preceding 8 months doing very little other than working through the implications of one paper. There is a conference banquet, and at the banquet, somebody has rewritten the words to a pop song that was, at that point, inescapable everywhere on Earth. The song is the Macarena, and what happens is that a room full of professional theoretical physicists, people who have spent their careers on quantum field theory and differential geometry, stand up and perform the dance, with new lyrics, in honor of Juan Maldacena, who is sitting in the audience. There is footage, people are laughing, somebody is doing the arm movements with real commitment. The chorus is about brains and duality and a black hole made of gauge theory. It is a very silly moment, and it is also the clearest possible indication of what had just happened to that field. You do not get that from a good paper. You get that from a paper that has reorganized what everyone in the room thought they were working on. And the silliness is what relief sounds like when several hundred people have all been thinking about the same thing for a year. Now let us come back to why any of this matters for the question we are actually asking tonight. Look carefully at what the two sides of the correspondence contain. On the boundary, 4 dimensions. A quantum field theory, no gravity. Nothing curved, nothing bending, no space-time dynamics of any kind, just fields on a fixed background, doing ordinary quantum mechanical things. In the bulk, 5 dimensions. Gravity, curvature, black holes, everything general relativity describes. And these are the same theory. Sit with the implication for a second, because it is the strongest single result in this entire story. If the two descriptions are genuinely equivalent, then everything in the 5-dimensional gravitational picture must be constructible out of the 4-dimensional non-gravitational one. There is nothing extra in the bulk. There cannot be, because the boundary theory is complete on its own. Which means the 5th dimension is not a fundamental ingredient of that universe. It is something that appears when you redescribe the boundary theory a certain way. And gravity is not a fundamental force in that universe either. It is what the boundary physics looks like when you organize it into the bulk language. An entire dimension of space, emergent, gravity, emergent, not as a philosophical suggestion or an interpretive stance, but as a mathematical fact about a specific, fully specified, extensively checked example. Before 1997, the claim that space-time might not be fundamental was a hunch supported by circumstantial evidence. After 1997, there existed at least one universe, written down in complete detail, in which it was demonstrably true. There is a practical consequence that is worth mentioning, because it does something important for the credibility of the whole business. The dictionary runs in both directions, and it has a very useful property. When the boundary theory is strongly coupled, meaning its particles interact so fiercely that the standard calculational methods break down completely, the corresponding bulk description is weakly curved and easy to handle with ordinary classical general relativity. Hard problems on one side become easy problems on the other. This turned out to matter to people who have no interest in quantum gravity at all. Nuclear physicists studying the quark-gluon plasma, the state of matter produced when heavy ions are smashed together at facilities like the relativistic heavy ion collider, found that their system was strongly coupled in exactly the way that defeats conventional methods. So they started using the holographic dictionary, computing with black holes in a fictitious higher dimensional space, and translating the answers back to get properties of a real fluid made of real quarks that had really been produced in a real machine. The results were not perfect, but they were useful, and they were useful in a regime where nothing else worked. Condensed matter physicists have done similar things with strange metals and with systems near quantum critical points, where the ordinary theory of electrons in solids stops describing what the materials actually do. The particular result people point to most often concerns viscosity. Using the holographic dictionary, physicists computed a lower limit on how thin and free-flowing a strongly interacting fluid can possibly be, expressed as a ratio between its viscosity and its density of entropy. The quark-gluon plasma produced in heavy ion collisions came out extraordinarily close to that limit, closer than any other substance ever measured, which is why it is sometimes described as the most perfect fluid known. The prediction came from doing general relativity in a five-dimensional space that does not exist, and it landed on a measurement made in a laboratory in New York. Condensed matter physicists have done similar things with strange metals and with systems near quantum critical points. That is a specific kind of evidence, and it deserves weight. When a mathematical correspondence starts being used as a working tool by people who are indifferent to its philosophical implications, and it keeps producing answers that match experiment, it becomes much harder to dismiss as an elegant coincidence. Now for the caveat, and it is a large one, and it is going to grow larger as the night goes on. Anti-de Sitter space is not the universe we live in. Anti-de Sitter space has negative curvature. It has a boundary at infinity, a kind of wall you can define things on, which is precisely what makes the whole construction possible. Our universe does not have that. Our universe has a small positive cosmological constant discovered in 1998, which makes it what is called de Sitter-like, expanding and accelerating, with no boundary of the required kind anywhere. So the one-worked example of emergent spacetime that physics possesses is an example in a universe with the wrong sign. Nobody has been able to write down a holographic dictionary for a universe like ours. It is not that people have not tried. It has been an active problem for a quarter of a century, and it is arguably the single largest open question in the field. Hold that. We are going to come back to it, and it is going to be one of the reasons the honest answer at the end of tonight is not a tidy one. There is a second caveat that gets less attention and deserves some. The correspondence gives you emergent space, and it gives it convincingly. What it does not obviously give you is emergent time. In the standard formulation, the time coordinate on the boundary and the time coordinate in the bulk are the same time. The dictionary builds up a spatial direction out of energy scales, but it does not build up time out of anything. Time is shared. It is already there on both sides, doing the same job. Which is awkward, because the deepest of the three quantization failures we walked through earlier was specifically about time. The Wheeler-DeWitt equation said the universe does not evolve. If the best worked example of emergent spacetime leaves time exactly where it found it, then the hardest half of the problem is still standing. Some physicists regard this as a technical gap that will close. Others regard it as a sign that space and time are genuinely different kinds of thing, and that our habit of saying spacetime as a single word has been quietly misleading us for over a century. Nobody has settled it. But even with that caveat, something had changed permanently. Maldacena had shown that a universe can have spacetime and gravity as emergent features rather than fundamental ones. The question was no longer whether it is possible. The question was, what specifically does the building? If the five-dimensional interior is constructed out of the four-dimensional boundary, then something in that boundary theory is the raw material. Something in there is being assembled into geometry. And for 13 years, nobody could say what. We were still not in a position to say what space-time is. The answer, when it arrived, came from a thought experiment simple enough to explain to somebody in a lift, and it identified the ingredient by name. Part 9. The thread that sews space together. In 2010, a physicist at the University of British Columbia named Mark van Ramsdonk wrote a short essay and entered it into the annual competition run by the Gravity Research Foundation. It won first prize. It was posted to the preprint server as a paper numbered 1005.3035, and it is, by the standards of theoretical physics, almost aggressively brief. He has said since that the central argument struck him as almost too simple to be new, which is very often what an important argument feels like from the inside. Here is what he did. Take the boundary theory, the four-dimensional one, with no gravity, that Maldacena showed, is equivalent to a five-dimensional universe with gravity in it. Now divide that boundary into two halves. Draw a line down the middle of it, conceptually, and call one side A and the other side B. The boundary theory is a quantum system, and quantum systems have a property that has no classical equivalent. The two halves are entangled. The quantum state of the whole is not simply the state of A alongside the state of B. There are correlations running across the division, such that measurements on A tell you things about B. This is not unusual. This is the generic situation for any quantum system you carve into pieces. It is worth being careful about what entanglement is, because it is the load-bearing concept for the rest of tonight, and it is routinely described badly. Entanglement is not a signal, and it is not a force, and it is not a connection in the sense of a string between two objects. It is a statement about description. When two systems are entangled, there is no complete description of one of them by itself. You can write down everything there is to know about the pair, and that description will be complete. And yet, if you then ask what state the first one is in on its own, the question has no full answer. The information is not stored in the parts. It is stored in the relationship. That is the property that makes it a candidate for building geometry. Entanglement is the only thing in physics whose natural home is between things rather than in them. If you were going to construct space out of some ingredient, and space is fundamentally about betweenness, entanglement is the only material on the shelf with the right shape. And there is a useful measure of it. Entanglement entropy is a number, computable, that tells you how much of a system's information is stored in its correlations with something else, rather than in itself. 0 means completely independent. Large means deeply intertwined. That number is going to turn out to be the same number as an area. Now Van Ramsdonk said, do something to it. Reach in and reduce the entanglement between A and B. Turn it down, gradually, towards 0. And while you are doing that, use the dictionary to watch what happens to the five-dimensional universe that this boundary theory describes. Let me put you at the controls. You are standing at a console. There is one dial, and the dial reduces the quantum correlation between the two halves of a boundary theory. In front of you is a display showing the bulk spacetime the theory corresponds to, which at the moment is a single connected universe, and running through the middle of it is a region joining the part that corresponds to A with the part that corresponds to B. You turn the dial down a little. The joining region narrows. Not shorter, narrower, as though something is being drawn in from the sides. You keep turning. It thins further. It becomes a neck, then a throat, then something like a thread. The two ends of the universe are still connected, but the connection is now barely there, and it is getting harder to see how anything could pass along it. You turn the dial to 0, and the thread does not stretch and snap the way a physical thread would, because there is nothing physical about it. What happens is that the two regions stop having any spatial relationship at all. They do not move apart. There is no gap between them, because a gap would be a distance, and distance is exactly the thing that has ceased to exist. What you are looking at is two separate universes, each complete, each with its own geometry, and no answer whatsoever to the question of how far one is from the other. Turn the dial back up, and they reconnect. That is the result. The connectivity of space is controlled by entanglement. Reduce the quantum correlation between two systems, and the space between them thins out. Remove it entirely, and there is no space between them, not because they have become infinitely far apart, but because the concept no longer applies. Van Ramsdonk drew the conclusion in a single line. Entanglement is what holds space together. And if that is right, then distance is not what you think it is. Distance is a measure of how weakly two things are entangled. Two systems that are strongly correlated are nearby. Two systems that are barely correlated are far away. Two systems with no correlation at all are not at any distance from each other. They are in different places in a sense so strong that there is no route between them. Now bring that into the room you are in. The wall across from you is a certain distance away, and you have always understood that as a fact about geometry. There is a gap. The gap has a size. You could measure it with a tape. But on this picture, the reason that wall is over there rather than here is that you and it are only weakly quantum mechanically correlated. The cup on the table beside you is closer. And it is closer because you and the cup are more strongly correlated than you and the wall. When you stand up and cross the room, you are not moving through a container. You are changing your correlation structure with everything around you. Distance stops being a gap and becomes a relationship, and there is something quietly unsettling about that, in a way that is hard to place at first. The gap between you and the far side of the room felt like the emptiest, most neutral, least involved thing in your entire experience. It was the absence of anything. It turns out to be the presence of a very specific quantity of quantum correlation, and if that quantity changed, the room would change shape. The formal version of this arrived 4 years before the essay, and made it quantitative. In 2006, Shinsei Ryu and Tadashi Takayanagi wrote down a formula relating the two sides of the dictionary in a very direct way. Take a region of the boundary. Compute its entanglement entropy, which is a number measuring how correlated that region is with everything else. Now go into the bulk and find the smallest surface that spans the same region. The Ryu Takayanagi formula says the entanglement entropy on the boundary equals 1/4 of the area of that minimal surface in the bulk, in Planck units. That should look familiar. It is the Bekenstein-Hawking formula again, 1/4 of an area, except now it is not about black holes at all. It is a general statement connecting quantum correlation on one side of the dictionary to geometry on the other. The area law from 1973, which had looked like an oddity about collapsed stars, turns out to be a special case of a much broader identity between entanglement and shape. Geometry is entanglement, measured in a particular way. The formula has been checked extensively and extended, and it does something the earlier arguments could not. It lets you go in the constructive direction. Given a pattern of entanglement on the boundary, you can work out what shape the bulk has to be, region by region, rather than merely asserting that some shape must correspond to it. People have used it to reconstruct pieces of bulk geometry from boundary data, and to show which parts of the interior are recoverable from which parts of the surface. There are regions of the bulk that no single boundary region can see, which can only be reconstructed by combining information from several, in a way that turns out to have a close mathematical relationship to the error-correcting codes used in quantum computing. That last connection is genuinely peculiar, and it has become an entire research direction of its own. Spacetime, in this picture, is not merely built out of entanglement. It is built out of entanglement, arranged in the specific redundant pattern that protects information against being lost, the same pattern engineers independently invented to keep quantum computers from forgetting things. 3 years later, in 2013, Maldacena and Susskind pushed the idea into its most memorable form, in a proposal usually written as a two-word equation, ER equals EPR. The letters are initials. ER stands for Einstein and Rosen, who in 1935 described a solution to the field equations that connects two distant regions of spacetime through a tunnel, which we now call a wormhole. EPR stands for Einstein, Podolsky, and Rosen, who in the same year, 1935, published a completely separate paper about quantum entanglement, arguing that it was so absurd that quantum mechanics must be incomplete. Einstein wrote both papers in the same year. He thought they were about different subjects. He disliked the second phenomenon so intensely that he called it spooky action at a distance and spent the rest of his life trying to get rid of it. Maldacena and Susskind proposed that the two papers describe the same thing. An entangled pair of particles, on this view, is connected by a wormhole, a very small one, and a completely useless one, in the sense that it is non-traversable and nothing can be sent through it, which is why entanglement famously does not let you signal faster than light, but a genuine geometric connection nonetheless. And a large wormhole of the kind Einstein and Rosen wrote down is what you get when you entangle an enormous number of degrees of freedom in the right pattern. Two of the most famous ideas in 20th century physics, written by the same man in the same year, turn out to be one idea he never noticed he had. There is a consequence of that identification which is worth following because it changes what entanglement feels like. If entangled particles are joined by a geometric bridge, then the reason entanglement cannot be used to send a message is not a rule bolted onto quantum mechanics from outside. It is a fact about the shape of the bridge. Wormholes of this kind pinch off too fast for anything to cross. The throat closes before a signal can get through. The prohibition on faster-than-light signaling, which in the standard telling is a slightly mysterious feature of quantum mechanics that just happens to hold, becomes a straightforward statement about geometry. Two of the strangest facts in physics, the spookiness of entanglement and the impassability of wormholes, turn out to be the same fact stated in two languages. Susskind has also argued that entanglement by itself is not the whole story, and this is worth knowing because it is a genuine open problem rather than a tidy ending. If you take two entangled systems and simply let them sit, their entanglement stops changing fairly quickly, and yet the wormhole connecting them in the bulk description keeps growing longer for an extremely long time afterwards. Something on the boundary side must be tracking that continued growth, and entanglement entropy is not it. The current best guess is a quantity called computational complexity, roughly a measure of how many elementary operations it would take to build the quantum state from scratch. Whether that identification is right is unsettled, but it is a reminder that even inside the most developed part of this picture, there are quantities in the geometry that nobody can yet match to anything on the other side. There is a third strand that arrived from an unexpected direction, and it is worth knowing because it makes the picture feel less like exotic speculation and more like something with a mechanism. In 2009, Brian Swingle was working with a computational technique used for simulating complicated quantum systems on ordinary computers. The technique goes by an acronym, MERA, and it works by organizing the entanglement in a quantum state, into a layered network. Pairs of nearby things are combined, then those combinations are combined, and so on upward through the layers, so that short-range correlations are handled at the bottom and long-range correlations near the top. It was invented purely as a practical tool. Nobody was thinking about gravity. Swingle drew the network out and noticed its shape. The geometry of the diagram, with its layers and its branching, and the way distances work within it, is a discretized version of hyperbolic space. Which is to say, it looks like a chunk of anti-de Sitter space, the exact geometry that appears in Maldacena's correspondence. A technique for bookkeeping quantum entanglement, when you draw it on paper, produces the geometry of a universe with gravity in it. That is either an extraordinary coincidence, or it is telling you what space is. On this reading, space is not a thing that entanglement happens inside of. Space is what a particular pattern of entanglement looks like when you draw it, in the same way that a map is what a set of distances looks like when you draw it. So the picture at this point in the story is roughly the following. The interior is built from the boundary. The building material is quantum entanglement. Geometry is a way of visualizing correlation. Distance is weakness of correlation. And the area law that started the whole thing is a general identity connecting the two. That is an enormous amount of progress from where we started. But notice what it still does not explain. None of it says why Einstein's field equations take the particular form they do. We have an argument that geometry is assembled from entanglement, and no account of why the assembled geometry obeys that specific set of equations rather than some other set. The thing that makes gravity gravity is still unexplained. We are still not in a position to say what spacetime is. And the answer to that last piece was published 2 years before Maldacena's paper, by a physicist who was not thinking about holography or string theory or extra dimensions, and whose argument fits in 4 pages. Part 10. It was thermodynamics all along. The paper is 4 pages long. It appeared in Physical Review Letters in 1995, in volume 75, beginning on page 1260. The author was Ted Jacobson at the University of Maryland, and the title is one of those titles that tells you exactly what the paper does if you already know enough to understand it, and absolutely nothing if you do not. Thermodynamics of Spacetime, the Einstein equation of state. It needs no string theory. It needs no extra dimensions. It needs no holographic dictionary, and no boundary at infinity. It was written 2 years before Maldacena's paper, and it does not depend on any of the machinery that came afterwards. And it is, in the judgment of a lot of physicists, the single strongest piece of evidence in this entire story. Here is the argument in full. Start with an observer, not a special one, just somebody accelerating through space-time, in any direction, at any rate. And notice something about acceleration that is easy to miss. If you are accelerating steadily, there are events you will never receive news of. Light from far enough behind you, emitted after a certain moment, will never catch up, because you are pulling away from it and continuing to pull away. There is a boundary behind you, a surface beyond which nothing can ever reach you. It is not a wall, and it is not a thing, and if you turned off your engines it would vanish. But while you are accelerating, it is there, and it functions exactly like the horizon of a black hole functions for someone outside. It is called a Rindler horizon, and every accelerating observer has one. Now add a result from 1976. Bill Unruh showed that an accelerating observer does not experience empty space as empty. The vacuum, to somebody accelerating through it, is warm. There is a genuine temperature, proportional to the acceleration, and an accelerating thermometer would register it. Let me put you inside this, because it is the strangest ordinary fact in physics. You are in a spacecraft, far from anything, and the engines are running at a steady rate. Out the window, there is nothing at all. No stars close by, no dust, no radiation source. By every measure available to somebody floating alongside you at constant velocity, you are moving through a perfect vacuum, and a perfect vacuum contains nothing. Behind you, though you cannot see it and there is nothing to see, a horizon has formed. It sits at a fixed distance behind your ship, keeping pace, and everything past it is permanently out of contact with you as long as the engines run. And in your hand, you are holding a thermometer of impossible sensitivity, and it is not reading 0. It is reading warmth, faint beyond any description, but present and steady, and it changes when you change the throttle. Push harder, and the reading climbs. Ease off, and it falls. Cut the engines entirely, and it goes to 0, and the horizon behind you disappears. The emptiness you are traveling through is not a fixed thing with fixed properties. Whether it is warm depends on what you are doing. The number is small enough to be almost comic. If you accelerate at 1g, the same acceleration you feel standing on the ground right now, the unroux temperature comes out to about 4 times 10 to the minus 20 Kelvin. That is 20 billion times colder than the coldest thing anyone has ever produced in a laboratory. Nobody has measured it, and nobody is close. To get an unroux temperature of even 1 Kelvin, you would need to accelerate at something like 10 to the 20 meters per second squared, which is a quintillion times harder than gravity pulls on you, and nothing made of matter survives that. But notice what the effect implies, even at 4 times 10 to the minus 20 Kelvin, because the size of the number is not the interesting part. Whether the vacuum contains particles is not a fixed fact about the vacuum. It depends on the motion of whoever is asking. 2 observers passing through the same point of empty space, one coasting and one accelerating, will disagree about how many particles are there, and both will be right. The concept of a particle, which feels like the most solid thing in physics, turns out to be relative to a state of motion. But Jacobson did not need to measure it. He needed to assume it. So here are his 2 assumptions, and there are only 2. The first is that the entropy associated with any horizon is proportional to its area. This is Bekenstein and Hawking's result, and Jacobson simply took it seriously for every horizon rather than only for black hole horizons. The second is the ordinary relation from classical thermodynamics that connects heat flow, temperature, and entropy. When heat flows into a system at some temperature, the entropy goes up by the heat divided by the temperature. This is the relation students learn in a first thermodynamics course. It is not exotic. It has been known since the 1850s. Jacobson's move was to require that this second relation holds across every local Rindler horizon, for every observer, at every point in spacetime, all the time. That is it. Those are the ingredients. Entropy proportional to horizon area, and the standard heat relation applied everywhere, for everyone. And out the other end come Einstein's field equations. Not approximately, not in some limit. The full equations of general relativity, the ones that describe the bending of light around the sun and the ringing of space-time after 2 black holes collide, derived as a consequence of thermodynamics. Now, why does that matter so much? Physics derives things from other things constantly. It matters because of what an equation of state is. An equation of state is a particular kind of law. The ideal gas law is 1. Pressure times volume equals a constant times temperature. It is accurate, it is useful, engineers rely on it, and it is not a fundamental law of nature. It is what emerges when you have an enormous number of molecules bouncing around and you stop tracking them individually and describe only the averages. Every quantity in it, pressure, volume, temperature, is a statistical summary of something you have deliberately stopped resolving. Here is the point that carries the weight of this entire episode. In the whole history of physics, an equation of state has never once turned out to describe something fundamental. Not one time. Whenever physicists have found a system obeying an equation of state, that system has turned out to be made of smaller things. That is what the mathematical form is telling you. Nobody derived the ideal gas law and concluded that gases are elementary. They concluded that gases are made of molecules, and they went looking, and they were right. Jacobson's own way of putting it is the comparison I asked you to hold on to earlier. Sound waves in a gas. Sound is completely real. You can hear it, record it, measure its speed, build instruments around it. There are equations that describe how it propagates, and they are excellent equations. But there is no such thing as a fundamental sound particle in the underlying description of the world. At the level of atoms, there is no sound. There are only molecules colliding, and sound is the name for what unimaginably large numbers of those collisions look like when you stop resolving individuals and describe the average. Jacobson's suggestion is that general relativity stands to whatever space-time really is exactly as the equations of sound stand to atomic theory, which would mean that gravitational waves are sound waves in something. Go back to that moment in Livingston, on the 14th of September 2015. The instrument detected a disturbance traveling through space-time, and physicists rightly regarded it as proof that space-time is a real physical medium with real degrees of freedom. On Jacobson's reading, that inference is correct, and it is also incomplete in a specific way. What LIGO heard was real. What it was a disturbance in is not the bottom layer, and that is where the flaw goes. We started tonight with the most reasonable assumption anyone has ever held, that underneath everything there is space, and it is simply there, being the place where things are. Newton called it absolute and immovable. Einstein made it flexible and dynamic and gave it energy of its own. And what Jacobson's derivation says is that the equations governing that flexible dynamic structure have the mathematical form of a summary, the form of a thing that is averaging over parts it is not showing you. The flaw is not a flaw. It is a surface tension. It is what an enormous number of something looks like from far enough away that you cannot see the something. There is an objection to Jacobson's argument that is worth taking seriously, because it is the one that bothers physicists most, and it is not easily dismissed. The horizons in the derivation are observer-dependent. Your Rindler horizon and mine are in different places if we are accelerating differently, and they vanish entirely for anyone coasting. So the entropy that Jacobson attributes to these horizons is not a property of a region of space-time. It is a property of a region relative to somebody. Two observers passing through the same point disagree about how much entropy is where, and neither of them is wrong. For some physicists, that is a fatal strangeness. Entropy is supposed to count something, and a count that changes depending on who is doing it looks like a category error. For others, it is the most interesting feature of the whole argument, because it suggests that the microscopic degrees of freedom of space-time are not sitting at locations waiting to be counted, and that our instinct to ask how much is there at a given place is itself a habit imported from the container picture we are trying to leave behind. Jacobson returned to the problem in 2016 with a refined version, framed in terms of what he called entanglement equilibrium in small causal diamonds, which recovers the field equations from the condition that entanglement entropy in a small region is at a maximum. It is a cleaner argument, and it ties the thermodynamic story directly to the entanglement story from the previous part. Two lines of reasoning, developed separately for 20 years, converging on the same statement. Eric Verlinde pushed in the same direction in 2010 from a different angle, proposing that gravity is what is called an entropic force. An entropic force is not a fundamental interaction at all. It is a statistical tendency that feels like a pull. When you stretch a rubber band, the force pulling it back is not an attraction between the ends. It is the fact that there are overwhelmingly more tangled configurations of the polymer chains than straight ones. So the system drifts toward tangled. and that drift feels like a force in your hands. Verlinde suggested gravity is the same kind of thing, not a force, but a statistical preference of the microscopic degrees of freedom of spacetime. That proposal has attracted serious criticism, including arguments that it conflicts with certain neutron interferometry results, and it is not consensus. But it belongs to the same family, and Thanu Padmanabhan spent much of his career developing a parallel program showing that the field equations of a whole range of gravity theories, not just Einstein's, can be written as thermodynamic identities. The point is not that any one of these is established. The point is that gravity keeps behaving like thermodynamics, from multiple independent directions, and physicists have never before encountered something that behaves like thermodynamics and turned out to be fundamental. There is even a laboratory version of the argument, and it deserves mentioning because it is the closest anyone has come to touching this experimentally. If you take a fluid and make it flow faster than the speed of sound within it, then sound waves in the fast-flowing region can never travel back upstream. There is a surface, at the point where the flow speed passes the speed of sound, beyond which sound cannot escape. That is a horizon in every functional sense. And when physicists build these systems in flowing water, and more precisely in ultra-cold clouds of atoms called Bose-Einstein condensates, they find that the analog horizon radiates. There is an analog of Hawking radiation, coming off a horizon made of nothing but a change in flow speed, in a fluid made of ordinary atoms obeying ordinary non-relativistic physics. Nobody thinks that fluid is really curved spacetime. That is exactly what makes it useful. It demonstrates, in a laboratory, that horizon thermodynamics is what emergent descriptions do. The thermodynamic behavior of a horizon does not require spacetime to be fundamental. It arises naturally when something spacetime-like emerges from something that is not. So the case, at this point, is as strong as it is going to get without an experiment. Quantizing spacetime fails in three ways. Its horizons carry entropy proportional to area, like nothing else in nature. That entropy is a general property of all regions, not just black holes. There is at least one complete worked example in which space and gravity are demonstrably emergent. The building material appears to be quantum entanglement, and the equations themselves have the mathematical form of a statistical summary of unresolved parts, which leaves exactly one question standing, and it is the one nobody can answer. What are the parts? Part 11. So what is it made of? There are serious answers to that question. The difficulty is that there are several of them, they disagree with each other, and not one has any experimental support. Loop quantum gravity gives the most direct answer, and it is worth noting that it answers a slightly different question than the one we have been asking. Developed from the late 1980s onward by Abhay Ashtekar, Carlo Rovelli, Lee Smolin, and others, it holds that spacetime is not emergent from something non-spatial at all. It is quantized directly, the way a field is quantized. Its central technical result is that the mathematical operators corresponding to area and volume have discrete spectra. Area does not come in a smooth continuum of possible values. It comes in steps, and there is a smallest non-zero area, on the order of 10 to the minus 70 square meters. The fundamental objects are called spin networks, graphs of nodes joined by links, where the nodes carry quanta of volume and the links carry quanta of area. Roger Penrose invented them in 1971 as a purely combinatorial exercise in building geometry out of angular momentum, decades before anyone found a use for them. So loop quantum gravity gives you granular space rather than no space. Space made of pieces is a different claim from space made of something that is not space, and it is worth keeping the two apart. Causal set theory goes further. Proposed in 1987 by Luca Bombelli, Juhan Lee, David Meyer, and Raphael Sorkin, It holds that the fundamental structure is a discrete collection of events, with nothing but an ordering, a bare record of which events could have influenced which others. No distances, no geometry, no dimensions. Just a list of what came before what. Everything else, including how far apart things are, and even how many dimensions the world has, emerges from counting elements. The program's slogan is that order plus number equals geometry, and it has one moment in its history that is genuinely impressive. In 1987, using this framework, Sorkin argued that the cosmological constant should not be zero, as almost everyone assumed at the time, but should be small and non-zero, with a magnitude set by fluctuations in the number of spacetime elements. 11 years later, in 1998, two independent teams studying distant supernovae discovered that the expansion of the universe is accelerating, which requires exactly such a small non-zero cosmological constant. The prediction is not precise enough to count as a confirmation, and honest causal set theorists say so. But it was made in advance, in print, from the framework, which is more than almost any other approach to quantum gravity can claim. Then there are the tensor network approaches, descending from Swingl's observation, treating spacetime as something closer to a circuit diagram than a substance. That is the honest state of play. Beautiful, mutually incompatible, untested. And now we come to the two problems that make the ending of tonight what it is. The first is the one I asked you to hold on to. The single fully worked example of emergent spacetime, Maldacena's correspondence, lives in anti-de Sitter space, which has negative curvature and a well-behaved boundary out at infinity that you can write information on. Our universe has neither. In 1998, we learned that our expansion is accelerating, which means we have a small positive cosmological constant, which puts us in a de Sitter-like universe with no such boundary anywhere. Nobody has written a holographic dictionary for a universe like ours. Not for lack of trying, it has been an active problem for over 25 years, and it is arguably the largest open question in the field. So the strongest evidence that spacetime is emergent comes from a universe with the wrong sign, and whether it carries over to the one we actually inhabit is unknown. The second problem is scale, and it is brutal. If spacetime has structure, that structure lives at the Planck length, about 1.6 times 10 to the minus 35 meters. The Large Hadron Collider, the most powerful instrument ever built for probing small distances, reaches down to about 10 to the minus 19 meters. The gap between the two is 16 orders of magnitude. To reach the Planck scale, by scaling up current accelerator technology, you would need a machine roughly the size of a galaxy. One direct attempt has been made. Craig Hogan proposed that holographic structure should produce a specific kind of jitter in space, a fuzziness that would show up as correlated noise between two interferometers sharing the same region. The Fermilab holometer was built to look for it, using two interferometers with 39-meter arms, and in December of 2015, it reported that it had ruled out Hogan's model to high statistical significance. It did not rule out the holographic principle, and Hogan proposed a modified version sensitive to rotation. But the first direct experimental search for the structure of spacetime found nothing. The most promising route forward comes from a different direction entirely. In 2017, two groups independently, Sugato Bose and colleagues, and Chiara Marletto with Vlatko Vedril, proposed an experiment that sidesteps the energy problem completely. Take two small masses, isolate them so that gravity is the only thing passing between them, put each into a superposition of two positions, and afterwards check whether the two masses have become entangled. The logic is clean. A classical field cannot create entanglement between two systems. If gravity alone entangles them, gravity is quantum. The experiment requires holding masses of around 10 to the minus 14 kilograms in superposition for seconds, while shielding them from everything else in the universe. That is beyond anyone's current capability by a wide margin. It is not obviously beyond it forever, and several groups are building toward it. One more thing, because it circulates constantly and attaches itself to exactly this material. You will hear that all of this proves we are living in a simulation. The argument runs that the area law shows reality has finite information capacity, that finite capacity means reality is digital, and that digital means computed, and computed means somebody is running it. Each step fails. A limit on information density is not the same as pixelation. Continuous theories can respect a holographic bound without being made of squares. And even where discreteness does appear, discrete does not mean computed. A crystal is discrete, and nobody is running it. The boundary theory, in Maldacena's correspondence, is a quantum field theory, which is not a classical computer and does not behave like one. The real finding is stranger than the popular version, which is usually how it goes. It says, the world may be built from information-theoretic ingredients. It says nothing whatever about whether anyone is doing the building. Every one of these programs, every experiment, every argument in this part, is an attempt to name the thing the descent found underneath, and none of them has managed it. Part 12. The deeper you look. So let us answer the question we started with, plainly, without softening it. The deeper physicists look into spacetime, the less they understand it. And that is not a complaint about the state of the field. It is the finding. It is the actual result of 120 years of looking, and it has a shape. Walk back down the staircase one more time and watch what happens at each step. At the top, there was a container, absolute, immovable, indifferent to its contents. That is what Newton wrote down, and it is what almost everyone still carries around without examining it. Look more closely, and the container becomes a field, flexible, curved, responsive, carrying energy, capable of ringing like a bell for 1.3 billion years after two black holes touch. That is more real than a container, not less. Look more closely still, and the field cannot be quantized. Not because the problem is hard, but in three separate structural ways that suggest it is the wrong kind of question. Look at its horizons, and they carry entropy, which is a thing only made-of-parts systems do. Count that entropy, and it scales with surface rather than volume, which nothing else in nature does. Take that seriously, and the interior of every region turns out to carry no independent information. Write down the dictionary, and an entire dimension of space, along with gravity itself, turns out to be a redescription of something with one dimension fewer. Ask what does the building, and the answer is quantum entanglement, so that distance is a measure of how weakly two things are correlated. And finally, write down the equations that govern the whole structure, and they have the mathematical form of an equation of state, the specific form physics has only ever encountered when describing something made of parts it was not resolving. 7 layers, and at every single one there was less space-time than at the layer above. That is what the title means, and it is worth separating what is established from what is suspected, because the difference matters. Established, in the sense that the mathematics is checked and the community broadly agrees, black hole entropy scales with horizon area. The holographic bound holds. The correspondence works, has been verified in an enormous number of specific cases, and is used as a practical calculational tool by physicists who do not care about any of these implications. Entanglement entropy on a boundary equals a minimal area in a bulk. Einstein's equations follow from thermodynamic assumptions, suspected and unverified, and possibly wrong, that any of it applies to the universe we live in, that the parts exist, that anybody will ever find them. 16 orders of magnitude below anything we can reach. One worked example, in a universe with the wrong curvature. One direct experiment, which found nothing. A set of candidate answers that contradict each other, and a proposed test that requires holding a speck of matter in two places at once for several seconds without disturbing it, which nobody can currently do. That is the honest position, and it is the position tonight ends on, because inventing a resolution would be a worse ending than not having one. It is worth asking what a resolution would even look like, since we are unlikely to see one soon. It would not be a photograph of the parts. Nobody is going to build a microscope that resolves the Planck length. What it would look like is a theory that starts from something with no space in it, derives Einstein's equations without assuming them, and then predicts one number that nobody had measured yet, and then somebody measures it, and it is right. That is the whole test. It is the same test atomic theory passed when it predicted specific patterns in how gases behave, and the patterns were found. Nothing in this field has passed that test. Several programs have come close to the first half. None has produced the number. That is not a small gap, and it should not be described as one. But before we finish, come back up, out of all of it, and sit where you are actually sitting. There is a floor beneath you. It has been there the entire time we have been talking, holding your weight, doing the one thing you have never asked it to justify. And you know now what physics can and cannot say about it. It can say the floor is made of atoms, and the atoms of nuclei and electrons, and the nuclei of quarks bound by gluons. All of that is solid ground, in the sense that we have measured it. What it cannot say is what any of that is sitting in, the space the atoms occupy, the space you occupy, the distance between your body and the ground. Physics can now tell you that this is very probably not a fundamental feature of reality. It is very probably an average, a statistical description of something with parts, obeying an equation of state, held together by correlations, and nobody on Earth can tell you what the parts are. You have spent your entire life with a confident and completely reliable sense of down. Every step you have ever taken has been an act of trust in it. And the current best understanding in physics is that down is a large-scale property of something that has no name. Which means, in the most literal sense the words will bear, that you have never stood on anything. You have only ever stood in a place where a great many unresolved things are behaving, on average, like a floor. And they will keep behaving that way. That is worth saying, because none of this is a warning. The average is extraordinarily stable. The ground will hold tomorrow exactly as it held today, and the fact that physicists cannot yet say what it is made of has never once caused anybody to fall through it. Water was still wet before anyone knew about molecules. So there is nothing to be afraid of here. There is only something to notice, and it is the kind of thing that is easier to notice lying still in the dark than at any other time. Every time we have looked more closely at the thing everything else rests on, we have found less of it and more of something else underneath, and then run out of instruments. The container became a field. The field became a projection. The projection became a pattern of correlations, and the correlations became an equation of state for parts nobody has ever seen. Each layer was more true than the one before, and had less in it. The deeper we look into spacetime, the less there is to find. Not because we are failing, because that is what is there. And somewhere below the last layer anyone has been able to reach, in a place 16 orders of magnitude beneath the smallest thing we have ever measured, the universe is doing something. It is doing it right now, underneath your chair, in the space between your hands, in every cubic centimeter of the room you are lying in. Whatever it is what everything else is made of. And it has been doing it, quietly and without interruption, for 13.8 billion years, waiting for somebody to work out how to look.